Okay, so for this first question then, what we've got to do is just integrate these three terms with respect to x. So they're nice easy terms, x to the power n type terms. So remember, all you've got to do is add 1 to the power and divide by the new power. So I've got the 2/3 then, x to the power 4 over 4 for this one when it comes to integrating that. For minus 6x to the half, just add 1 to the power. That's x to the power 1/2, better written as 3 over 2. Divide by the new power, 3 over 2. And then for the constant, just add an x to it. Well, don't add an x to it, just multiply the 1 with an x if you like. Okay, so that just gives us the x. And don't forget that constant of integration. So just cleaning this up, you should find you get these three terms plus the constant of integration. Okay? Now for question 2 part 1, we had to show that this quadratic expression was greater than 0 for all real values of x. And as you can see, what I've done here is completed the square. Remember that what you've got to do is put x in brackets and halve the coefficient of x here. So half of minus 8 is minus 4. If you square that, okay, when you open that bracket up, you'd end up with x squared minus twice the product, that'd be the minus 8x there, but you'd get minus 4 all squared, which would be plus 16. So what I've done is take away 16. So these two terms would now give me just x squared minus 8x, and then I put that plus 17 on the end. So simplifying these two, you can see you get plus 1. And this has to be greater than 0, has to be positive for all real values of x, because this term here is squared, so it's always going to be positive. You're adding another positive number to it, so the sum of two positive numbers always going to be greater than 0. Okay, if you're unsure on how to complete the square, do go back and check out my tutorials on that. Okay. Okay, so for this part of the question then, we're asked to show whether a particular statement is always true, sometimes true, or never true. That statement being that if we take a number, a real number, x, say, then if you add 3 to it and square that result, it's always greater than the original number squared. And what I've got here are two methods that I've used. This is the algebraic method where I set up this inequality, and if you work this through, square this bracket out, you get x squared plus 6x plus 9, which is then greater than x squared. Subtract x squared from both sides, leaving you with 6x plus 9 is greater than 0. Take 9 from both sides, divide by 6, and you end up with x is greater than minus 9/6, which if you divide top and bottom by 3, leads to minus 3 over 2, or minus 1/2. So x has got to be greater than minus 1/2. So it's not true for all values of x. But it is sometimes true, as you can see, if x is greater than minus 3 over 2. This alternative method, what I've done is I've taken a value of x, let's say 0, you can try other values, and if you set up this inequality, our number is 0, add 3 to it, square it, is it greater than the original number squared? Well yes, 3 squared is 9, it's greater than 0, so that's true. But if you take x is, say, minus 4, then minus 4 plus 3, that leaves us with negative 1. You square it, it's going to give us 1. Is it greater than the original value, minus 4 squared? Well, that comes to 16, and clearly 1 isn't greater than 16, so it's not true. And that would be sufficient then to say the statement then is sometimes true. Okay, so for this part of the question then, fairly straightforward. we're given the position vectors of A and B, and notice I've written them as O to A and O to B, okay, because they always start from the origin. And you'll notice I've also made a sketch here of our vectors, okay. So if we've got to work out the vector A to B, then in the usual way, going from A to B is going back down from A to O and then O to B. So you can look at this as minus O to A, because going the opposite direction, plus O to B. Standard result, O to B minus O to A. So all I've done is subtract those two vectors from one another, and you get this result, minus 9i plus 3j. Now for 3 part B, we've got our vector A to B, minus 9i plus 3j, and asked to find the magnitude of it. And this is just a simple case of using Pythagoras' theorem. So we just need to square our components, add them together, and then square root. So if you do that, you don't need the negative 9 here, you can just take the magnitude of that. So I'll put it as 9. So if you square our values out, you're going to get the root of 90. And we've got to give it in the simplest form, so you can see that I've split this into 9 times 10. We can take the square root of 9 as 3, and so we get the exact value, 3 root 10. Remember that when you're doing the square root, normally it would be plus or minus, but when you're finding the magnitude of a vector, it is just a positive value. Okay? So for question 4 then, we're given these two lines, L1, and we're told that the second line, L2, goes through these two coordinates. And so if we're to see if the lines are parallel, perpendicular, or neither, what we've got to look at then is the gradients of each of these two lines. If they're parallel, they'll share the same gradient. If they're perpendicular, the product of the gradients should be -1. And if neither of those cases exists, then the lines will be neither parallel or perpendicular. So you can see that for L1, what I'm going to do is rearrange this equation into the form y equals mx plus c, where m is the gradient. And you can see that I've added 3x to both sides, leaving me with 4y equals 3x plus 10, and then divided through by the 4, and that leaves me with y equals 3/4 x plus 10/4. M, the gradient, is clearly 3/4 then. So that's that one. Now we work out the gradient of L2, and when you're going between 2 points, then what we need to do is the difference in the y coordinates divided by the difference in the x coordinates. So I've started with this -1 here, so the difference in the y coordinates becomes -1 minus that 8, and then it's divided by the 5 minus -1, the difference in the x coordinates. You could do it the other way around, that is start with this y coordinate, 8 minus -1, divided by -1 minus that 5. You'll end up with exactly the same answer, -3/2. Okay, now you can see that clearly they share different gradients, so they're not parallel. But if you were to multiply these two gradients together, you'd find you don't get -1, you get -9/8. Okay, so the lines are not perpendicular. So in answer to our question, they're neither parallel or perpendicular. Okay. Now for question 5a then, we're given this equation and asked to come up with two errors that were made. And the two errors are on this line here and on the bottom line here. So for this one here, the error is that the person doing the sum has thought of the subtraction rule, this rule here, but you've got this 2 in the front. You're not allowed to have a number in the front of any log if you're going to use the subtraction rule. So therefore, we don't get this result here. We must deal with that 2 first, which by the power rule would have given us the log in base 2 of x squared. Then we could have gone on to use this particular rule. And the other mistake then is when it comes to undoing this log, taking the anti-log, as some people say. What it is that x would be equal to the base 2 raised to the power 3, not 3 squared, okay, as I've tried to demonstrate here. So if you've got the log of x in base 2 equaling 3, then it's x that equals the base 2 raised to the power 3, 2 cubed, okay? So for 5b then, we've got to give the correct solution to this equation. So as we said earlier, the mistake that was made in the previous part was to not remove this 2. So by the power rule for logs, we must remove the 2 first of all, and it becomes x to the power 2x squared. That gives us 2 log terms here, which we're subtracting from one another. So we can use the rule that is the log of 1 divided by the other value. So in other words, just the log in base 2 of x squared divided by square root of x. And if you work that out by subtracting the powers, you're going to get x to the power 3 over 2. And then we need to remove the log here. We anti-log or take the inverse to both sides, and we end up with x to the power 3 over 2 equals that base then 2 raised to the power 3, not 3 to the power 2, which was the mistake in the previous part of the question. So we end up with x to the 3 over 2 then equals 2 cubed, which is 8. And then what I need to do is square both sides and take the cube root. Okay, so that's going to give me x equals 8 to the power 2/3. Cube rooting 8 is 2. Square it then is going to be 2 squared, which is 4. Okay. So for this part of the question then, we're given the equation for the profit P against the selling price X of the toy. I'm asked to say why X equals 15 pounds is not a sensible price to sell the toy for. So you just got to substitute X equals 15 into our equation here, and what turns out is a negative value, minus 125. Remember, P is the profit in thousands of pounds, so what we end up with is it's not sensible, as the company would clearly make a loss of £125,000. Okay? So for 6 part B then, what we've got is that the company makes a profit of £80,000, and that means that P is equal to 80. We've got to be careful because it's not 80,000. Remember, P is measured in thousands. So P would be 80. And we've got to work out then the least price, the least selling price that we can produce that toy for. So you'll notice from the graph here, I've just taken the graph for P and I've marked in where P is 80, and you can see it crosses at 2 points, and we're interested at this point here. We've also got to be very careful at the end as well. So let's just work this through. We've got to substitute then P equals 80 into our equation and solve it for X. So I've just substituted that 80 in, and you can see then what I've done is just changed the signs on each term. Okay, you don't have to do that. I just decided to do it so that I kept this term positive. I've multiplied each term by -1. And then all I've done is add the 100 to both sides. That's given me the 20 there. And then divided through by 6.25, giving me x minus 9, I should say, squared equals 3.2. And then taking the square root to both sides, we end up with x minus 9 is plus or minus the root of 3.2. And then I add 9 to both sides, leaving me with x equals 9 plus or minus the root of 3.2. And it's this point that we're looking for the least selling price. So if you took the plus option, it would give you this value over here, which is a much larger selling price to achieve that 80,000. Okay, so we just want this one, which is the negative value. And if you work that out, you're going to end up with 7.211 and so on. Now, don't take this to 2 decimal places or anything. That would be 7.21. This is the catch. We want the least selling price. So what you've got to do in order to make at least an £80,000 profit is to take a value that is going to give us a value above this blue dot here. And that comes from going slightly more than 7.211, £7.22 in other words. Okay, so that would be a point just to the right of that dot on the x-axis. When you project up here, it's going to give us a profit of more than £80,000. Okay, so a couple of points there using 80 and this 7.22. Okay. Now in this last part of the question, 6c, we need to then state the maximum profit and the selling price of the toy to achieve that maximum profit. And you can see that our equation here contains 2 terms, the 100 minus this term here. And this term is always going to be positive, so you're going to be taking a value away from 100. So the maximum this can be is that 100 there when x equals 9, because that would make this term 0. Okay, so that maximum profit then is not 100, but remember p is measured in thousands, so that's going to be £100,000, and it's achieved when x equals 9. So that selling price of the toy is £9. There's no need to resort to differentiation to try and work out the gradient at any point on that curve and set it equal to 0. It's very quick, okay, as hopefully you've been able to see. So for this question then, what I've done is I've just sketched out 2 possible triangles. They're not accurate, but just to demonstrate that we are going to arrive at 2 values of theta, and obviously then 2 values for cosine theta. So we're given the area then of the triangle ABC is 15 centimeters squared and asked to find those 2 values for cos theta. So what I've done is looked at the area of a triangle, and we can use the formula half the product of 2 sides times the sine of the included angle. So in both of these triangles, it's going to be half of the product of those 2 sides, the 5 and the 10, times the sine of that included angle, whether it's this triangle or this triangle. And then clearly you can see that 10 times 5 is 50, divided by 2 is 25, and so I've divided both sides by 25, and that leaves me with sine theta equals 0.6. Or you could leave it as a fraction, obviously 3/5. And then to get those values of cosine theta, I pick up on the identity you should be familiar with. It comes from cos squared theta plus sine squared theta is equivalent to 1. But I've rearranged it to give me cos squared theta equals 1 minus sine squared theta. Substitute our value for sine theta in, ends up with 0.64. We take the square root, don't forget it's plus or minus, and the square root of 0.64 is 0.8. So we end up with either the decimal version, plus or minus 0.8, or you could work it out leaving it as a fraction, plus or minus 4/5. Okay? So in this question then, 7 part B, we're asked to find the longest length BC. And to do this, what we can use is the part A value for cos theta. It was plus or minus 0.8. And what I'm going to use is the cosine rule. So BC squared, the side opposite the angle, doesn't matter which triangle you're using, is equal to the sum of the squares of the other two sides minus twice the product of those two sides times the cosine of the included angle. If you're unsure of the cosine rule, do check out my videos on this. So just substitute your values in, as I've done here, and for cosine theta you can see I've substituted plus or minus 0.8. And we're looking for the largest value that gives us the longest length BC. Well, if you take the positive value of 0.8, you end up with 45, and if you take the negative value, you end up with 205. So we need to take that 205 and square root it then to get the largest value for the length BC. And we've got to leave it in exact form, so it's going to be equal to the root of 205, and the units would be centimeters. Don't forget those, okay? Just the root of 205 doesn't tell us anything. Okay, so for 8a then, part 1, we've given this equation here for the cost of running the lorry in pounds when it's travelling at v kilometers per hour, and we've got to find out the value of v which minimises that cost, and then go on to work out what that minimum cost would be. So in order to do this, we're going to need to differentiate this equation with respect to v, put it equal to 0 so that we find the stationary point, solve that equation, it will give us v, and then once we've found v, we can substitute it back into here to get the cost. And that's what I've done here. Before we can differentiate it, you'll notice I've brought this v up to the top, 1500, then v to the power minus 1. And it's now ready for differentiating. So in the usual way, you can see when we differentiate this term, the power goes out to the front here, multiply it with the 1500, minus 1500 v, and reduce the power by 1 to the power minus 2. And then we've got this one just simply is the 2/11. Constant differentiates to 0. So we need to put this equation equal to 0 at a stationary point. You'll notice I've rewritten the v to the minus 2 as 1 over that v squared. Okay, so you end up with minus 1500 over v squared. And then subtract, I should say add 1500 v squared to both sides, and you end up with this equation. Multiply both sides by 11v squared, and you get this. And then dividing by 2 to both sides, v squared equals 8250. Square root, no need for plus or minus here because that v is going to be a positive value, it's the speed. Okay, so it turns out to be 90.829 and so on. I've rounded it to one decimal place, 90.8, and don't forget those units, kilometers per hour. And to get that cost, I've not put the rounded value in, I've put the unrounded value into our equation and worked it through, and you can see it comes out to 93.028 and so on, which to the nearest pound is 93 pounds. Now for 8 part B then, we've got to show that that cost C is a minimum by considering the second differential of dc by dv. So I've taken dc by dv from the previous part. We differentiated again with respect to v in the usual way. Minus 2 times the minus 1500 gives me 3000, and then we drop the power by 1, so that's v to the minus 3. That constant differentiates to 0. So tidying this term up gives me 3000 over v cubed. And then we just need to substitute that value of v we found in the previous part of the question, substitute it into here, comes out at 0.004 and so on, which is a positive value. And you should be aware then that if this double differential is a positive value, then that signifies that you've got a minimum. Okay, so just to summarize, therefore C is a minimum when V equals the 90.829 and so on. Okay. So for this last part then, we've got to state one limitation for the model. And we're driving, it says, from London to Newcastle at a steady speed. Well, it's not going to happen, is it? You're going to come across hills, junctions, traffic lights. You're going to make fuel stops, I'm sure. Even if you're tired, you're going to make a stop. So you're not going to stay at a steady speed. So basically, the lorry cannot be driven then at a steady speed from London to Newcastle. So for this question then, we're given g of x equals this equation here and asked to show then that x plus 2 is a factor of g of x. And to do this, you've got to do the factor theorem. You've got to be aware that if we substitute x equals minus 2, not 2, we make this bracket equal to 0, so x would be equal to minus 2, substitute it into here and hope that it comes out to 0. If it does, then that would prove that x plus 2 is a factor of g of x. So if you're unfamiliar with the factor theorem, do check it out, okay, in my tutorials. Substitute minus 2 in and you'll find it does come to 0. So don't forget to state then that therefore x plus 2 is a factor of g of x. Okay? Now for question 9b, we've got to factorise g of x to write it in this form here and work out those values of a and b. And the method I'm doing here is an inspection method. There is another method which I'll show you after this section. It's the division method, so you might want to check that one out. So what I've done here is just written this out, as you can see, and now obviously if you were to square this bracket out, what you'd get is a quadratic of the form ax squared plus bx plus c. And we can easily see that the a here has to be a 4, because when you multiply the x with ax squared, that's the only term that's going to be in x cubed, and it's got to turn out to be 4x cubed, so a is going to be clearly 4. And also when it comes to looking at the constants, the only constant you're going to get in expanding this comes from when you do 2 times the constant on the end here. So 2c would come to that 50 there, so c would clearly be 25. Now when it comes to working out b, there's 2 ways you could do this. What I've done is looking at comparing the x squared terms. You're going to get x squared terms when you do x times the bx, that's going to give us bx squared. I've put it up here. And you're also going to get an x squared term when you do 2 times the 4x squared, which will give us 8x squared. So we've got bx squared plus 8x squared must be identical to the minus 12x squared we have up here. So that means that if we subtract 8x squared from both sides, bx squared would be minus 20x squared, so b would be minus 20, which I filled in there. And this goes on to be factorised as a square of 2x minus 5 all squared. And those values for a and b were integers. A was the 2 and b would be the minus 5 when you compare it to this bracket up here. Now you didn't have to just compare the x squared terms. You could have got exactly the same answer if you compared the x terms. I haven't shown the working out here, but I leave it to you to check out the x terms if you like, and you should find that b comes out to minus 20. Okay? So for 9 part B then, we've got to show that g of x can be expressed in this form. And in the previous section, I showed you another way of doing this, the inspection method. So if you haven't seen that already and want to try that out, do go back in this video. So I'm going to show you the algebraic long division method here, which is an alternative method that might suit your style. So in order to get ax plus b all squared, I need to take g of x and divide it by x plus 2, as you can see here. And we carry out algebraic long division then. If you're unsure of this, do check out the video tutorials I've got on algebraic long division. It's quite lengthy. I'll just briefly explain. What we do is we find a value that you multiply the x by to give the 4x cubed, and it's that 4x squared there. So you do 4x squared times all of x plus 2, and that gives you 4x cubed plus 8x squared. You take it away to find out what the remainder is, and it turns out that minus 12x squared minus that plus 8x squared is minus 20x squared. You bring down the next term, minus 15x, and you repeat the process again. What do you multiply the x by to give that minus 20x squared? It is that minus 20x. So you do minus 20x times x plus 2, and it gives you minus 20x squared minus 40x. And again, you subtract to work out the remainder. And you end up with that 25x. Bring down the next term, the 50. What do you have to multiply the x by to get the 25x? And it's just 25. So you do 25 times x plus 2 gives you 25x plus 50. And you subtract, and that's great. You get 0 remainder, which is what you would expect, okay, if we're to show that this is, or knowing that x plus 2 is a factor. Okay, so we take the quotient here, okay, 4x squared minus 20x plus 25, and we can write it in as being multiplied with the x plus 2. And this factorises to 2x minus 5 all squared. Has that form then, ax plus b all squared, where a is 2 and b is minus 5. Okay, so hope you're able to follow that, okay, if it caused any problem. So for 9 part C then, we're given the graph of g of x. We've seen that it factorises to this, and we've got to solve then g of x is less than or equal to 0 in part 1, and then go on to do in part 2 g of 2x equals 0. You can see my answers here, but I'll explain anyway how we go about it. What we've got here is that if we were to put this equal to 0, it would tell us where it crosses the x-axis, and clearly x is minus 2 when this factor equals 0. And this is a repeated factor, so that would mean that the curve is just touching the x-axis. We can see that because it's drawn, but if it wasn't drawn, repeated factors are always where a curve touches the x-axis. So this is going to be when 2x minus 5 equals 0, and that's going to lead to x equals 5 over 2, 2.5. Okay, so I've marked those points in, and so clearly when g of x equals 0 or is less than or equal to 0, well, clearly it's equal to 0 at 5 over 2, 2.5. But when it's less than or equal to 0, then you're looking at the values of x that you have to put in that give this as a negative value, in other words below the x-axis. So it's going to be values of x that are less than or equal to the minus 2. And when it comes to working out the values of x for which g of 2x equals 0, then you've got to be aware that when you have a 2x here, what it does to the original graph is it stretches it by a scale factor of 1/2 parallel to the x-axis, with the y-axis being invariant. Or in simple terms, it just kind of squashes this from the right hand side and the left hand side to the y-axis, and it halves these two values that you see here. So minus 2 then goes to minus 1, and 5 over 2, if you halve it, goes to 5 over 4. And where does it equal 0? Well, those points where it crosses the x-axis then at minus 1 and 5 over 4. Now for question 10 then, we've got to show that if we were to differentiate x cubed then by first principles, it's going to turn out to be 3x squared. And just as a reminder, if you've got y equals some function of x, then either dy by dx or f dash of x is equal to the limit of f of x plus h minus f of x all divided by h as h tends to 0. So I've let f of x equal x cubed. So when it comes to f of x plus h, just replace the x with an x plus h, and you're going to get x plus h all cubed. And then I look at using this formula here. So f of x plus h then is x plus h all cubed, then minus f of x, which is x cubed, and it's all divided by h. So I've next expanded x plus h all cubed. I've done it by using the binomial expansion here. You might want to take your time over expanding this, but remember, using Pascal's triangle, you get the coefficients as being 1, 3, 3, 1, okay? And then you start off with the highest power of x as x cubed, to agree with that power there, and you then reduce it by 1 in each term. This is x to the power 0 here, by the way, or simply 1. And the h, you do h to the power 0 here, h to the power 1, h to the power 2, h to the power 3. So I'm assuming anyway that you're familiar with using Pascal's triangle to expand x plus h all cubed. Okay, and then we've got minus x cubed on the end, all divided by h. The x cubes cancel, leaving me with this expression on the top here, and then I can divide each of these three terms by h, and that gives me this result here, 3x squared plus 3x squared h plus h squared. And now what I do is I let h tend to 0, so these two terms will disappear, just leaving me with 3x squared. Okay, so there's a very standard question. Do check out videos on differentiating by first principles if you've got any problems there. So for 11 part A then, we've got to use the binomial expansion to expand 2 minus x over 16 to the power 9 up to the first 3 terms. So I'm assuming that you're familiar with the binomial expansion. Again, if not, just check out my video tutorials on this. So using the binomial expansion, start with the power 9c0, then it goes to 9c1, 9c2 and so on. We take the first term in the bracket, 2 in this case, raise it to the power 9 and then reduce it by 1, 2 to the power 8, 2 to the power 7. And then we take the second term here in the bracket, minus x over 16, start off with minus x over 16 to the power 0, then start increasing it by 1 each time, minus x over 16 to the power 1, minus x over 16 to the power 2. And you should be able to find the NCR button on your calculator. Do check out how to use it. I've got videos on that as well. Work out 9c0 comes to 1. Anything c0 is always 1. nc1 is always n. 9c1 is 9. 9c2, do it on your calculator, comes out to be 36. And you'll see I've written purposely each of these values in the brackets here so you can check them out, okay? And then just expand them, okay? Simplify them, and that's what you get. The first 3 terms then, 512 minus 144x plus 18x squared, plus and so on. Don't forget this, okay? I always feel that you should write that in, and also the identical sign. Now in this part, for 11 part B and part C, we are given that f of x then is a plus bx all times the 2x minus x over 16 to the power 9. And we've got to work out the values of a and b given that the first term is 128 and the second term is 36x. So how do we do this? Well, I've written down what we found in the previous part for the expansion of 2 minus x over 16 to the power 9. And all we need to do is just look at expanding only parts of this. If we're looking at getting the first few terms, the first 2 terms anyway, we take the a, and you can see a times 512 gives me 512a, and a times the minus 144x gives me minus 144ax. I don't need to go on and do a times 18x squared. And then we've got bx times the 512. That's going to give me plus 512bx. I don't need to carry on and do bx times the minus 144x. That's going to be an x squared term. So that's as far as we need take it. And then all I need to do is just compare this to what we're given. So if we compare these two constants, you can see that 512a must be equal to that 128. You can solve that and you get a as a quarter. Now when it comes to working out the value of b, I just need to compare the coefficients of x, these two terms here, and equate it to the 36. And that's what I've done here, knowing that a is a quarter from the previous part. You can see I've substituted that in and just cancelled here, giving us minus 36. Add 36 to both sides, you're left with 512b equals 72. And if you divide both sides by 512 and reduce it down, b turns out to be 9/64. So there's our 2 values then for a and b. Okay? Okay, so for this question, 12a, we're given this equation here and asked to show that it can be transformed into this equation. So how do we do it? Well, what I've done is taken tan theta here. You should be familiar with the fact that it's sine theta over cosine theta. So Once we've done that, I've multiplied through by cosine theta to both sides, and that gives us this result. And we can now pull on the identity that sine squared theta plus cos squared theta comes to 1. So if you rearrange that, sine squared theta is the same as 1 minus cos squared theta. So I've got an equation now, all in terms of theta. I just need to expand this bracket, which I did down here, and then just add 2 cos squared theta and subtract 2 from both sides, and that takes me to the equation that we had to prove. Now for 12 part B, we're given this equation here, 4 cos 3x minus 1 equals 2 sine 3x times tan 3x, and we've got to use the previous part of the question to help us solve it, giving our values of x that are greater than or equal to 0 degrees but less than 90 degrees. So how does this compare with part A? Well, I've jotted down part A here, and can you see that this is exactly the same? It's got the same pattern, the same format if we let theta equal the 3x. And if we do that, remember in part A we showed that this could be reduced down to this quadratic equation in cos theta. Well, that means that if we let this 3x be theta, we can state this equation. And this equation factorizes. Factorizing, you get this, and then we can put each of these factors equal to 0. And by putting 3 cos theta minus 2 equal to 0, you can see that theta turns out to be the inverse cos of 2/3, or in other words, 3x is the inverse cosine of 2/3. And if you do a similar thing for this factor, 2 cos theta plus 1 equals 0, you end up with 3x equaling the inverse cos of minus a half. Okay, so I'm going to take each of these equations and solve them separately. So when 3x equals the inverse cosine of 2/3, if you use your calculator in degrees mode, inverse cosine 2/3, you'll end up with 48.18 and so on degrees. And you can see that I've drawn a quadrant diagram here for the 2 possible positions where cosine is positive, in the first quadrant and the 4th quadrant. Now, we've got our solution in the first quadrant, but if I was to work out this green 3x by doing 360 degrees minus the 48.18 and then dividing by 3, we're going to find that we've got an answer that is greater than 90 degrees. So all I need to do is just consider this one here, and if I now divide through by 3, you can see x is 16.06 and so on, which when rounded to 1 decimal place, as we were asked, then that's going to be 16.1 degrees. Now when we look at 3x equaling the inverse cosine of negative a half, then cosine is negative in the second and third quadrants. And I've marked those in here, okay, as possible solutions. So when you inverse cosine negative a half, you end up with 120 degrees on your calculator. So that's that 3x. The other 3x is going to be 180 degrees plus this little angle in here, which is 60 degrees. 180 minus that 120. Okay, so this 3x turns out to be 240 degrees. And if you divide each of these two answers by 3, you end up with angles in the range 0 to 90 as being 40 degrees and 80 degrees. So there's our solutions, that one there, 16.1 degrees to 1 decimal place, and these two exact ones, 40 degrees and 80 degrees. Now if you're unsure of using the quadrant diagram, do check out my tutorials on these. Okay, so hope you've been able to follow that example if it caused you any problems. So with this question, 13a, we're given this equation here, v equals p times q to the power t, and asked to compare it when we use logs to this equation and work out the values of p and q. So you've got to be familiar with your log rules here. So what we do is we log both sides to base 10. So you can see I've done that. And then we use the addition law. And that is that we can see this as the log of p in base 10 plus the log in base 10 of q to the power t. Don't make the common mistake of bringing that t out to the front here first of all. You must do it in this order. Now we can bring that t out to the front of this term using the power rule for logs. So that gives us this line here. You'll notice I've switched the terms round because this now compares with what we've been given. And we can just compare these terms and work out our values for p and then q. So if I look at the n value here, you can see that the log of p in base 10 must be equal to 4.8. And so I've written that in here, and to get p, we just take the inverse log or anti-log to both sides, and we end up with p equaling the base 10 to the power 4.8. And if you work that out on your calculator, we're asked to give the result to 4 significant figures. It turns out to be 63,100. And when it comes to working out the value of q, then you can see that the log of q in base 10 compares with the 0.05 here. So do a similar thing, that is anti-log both sides, and you get q equals 10 to the power 0.05. That gives us this result, which when rounded to 4 significant figures, q is equal to 1.122. Okay? So for 13 part B then, we've got to give interpretations for the value of p and the value of q. Well, we can get p very easily, and that's when t is 0, v will equal p. So that's saying that initially, when t is 0, that's going to be our initial value. That's on the 1st of January 1980. v will equal p. And we found out in the previous part that the value was 63,100. Okay, that was the original cost. And when it comes to working out what q was, remember we found out in the previous part that q turned out to be 1.122 and so on. And what that is a increase. The value increases each year, year on year, by 12.2%. This would be the multiplying factor, 1.122, which if you were to increase something by 12.2%, you would multiply it by that scale factor. Okay, so hope you're able to see your way through on that one. Now in 13 part C, we've now got this formula. I've replaced p with the value we found and q the value we found. I've used the unrounded values, and we've got this to the power t. So we've got to find out the value then on the 1st of January 2010, and that's going to be 30 years later. So we would set t equal to 30. Set t equal to 30, get on your calculator, work this out. We have to give it to the nearest £100,000, and it turns out to be £2 million. So 14a then, This is a typical question where you're given the equation of a circle in this form and asked to find the centre and radius. So do check out my tutorials on this. It's a very standard method. What we do is group together the x squared and the x term here. I've written this in red, and we do much the same for the y parts, y squared plus 10y. Group those together and we complete the square on each of the red parts and the blue parts. So completing the square then, you should be familiar with this. If you were to expand this bracket out, you're going to get x squared minus 6x plus 9. But we subtract the 9 to give us x squared minus 6x. So remember, we're halving that coefficient of x there. Half of minus 6 is minus 3. Do the same here, halve the coefficient of y, the 10 gives us the 5. Okay, so expand that out, you're going to get y squared plus twice the product, 10y, okay, plus 25, 5 squared. Subtract the 25 and you got y squared plus 10y. Okay, now all we need to do is add 9 and add 25 to both sides, and you end up with this result here. And when you compare this to the form of a circle, the centre of the circle is given as 3, negative 5. Okay, just change the signs that you get here. And remember, the radius squared is the 25, so the radius itself will be the square root of 25, which is 5. Don't go putting plus or minus here. Obviously radius is a length, it's got to be positive. Alright, so hope you are able to do that one. So for question 14b, what I've done is we've taken the equation of the circle. Remember, we found in the previous part, and I've sketched it here, it was a circle with a centre of 3, minus 5 and a radius of 5. So clearly it's going to touch the x-axis because this distance here will be 5 units. And we're given then the line y equals kx and told that it intersects the circle in 2 distinct points. And we've got to find out the range of values for k. Well, I've added to the diagram this brown line, y equals kx. You can see that k would have to be a positive value, that would be the gradient here, for it to cut in 2 places. Or you could get this set of values of k that are negative, this line y equals kx cutting in 2 distinct places. So what this really revolves around is solving simultaneous equations. I'm going to substitute y equals kx into this equation, form a quadratic equation in x, and then we're going to use the fact that the discriminant of a quadratic equation, for it to have 2 distinct roots, remember the b squared minus 4ac part, the discriminant of the quadratic, must be a positive value, must be greater than 0, and then we'll be able to solve that inequality, which I've done down here, and it will get us our results, which you can see here. But I'll take you through this, okay? So I've numbered my equations, obviously 1 and 2, as you can see, and I've substituted 2 into 1. And if we do that, we get this result here. And I've grouped up the x squared terms and the x terms. And now remember, this has the form of a quadratic, ax squared plus bx plus a constant on the nc equaling 0. So we know that for 2 distinct roots, 2 different solutions, in other words, that discriminant b squared minus 4ac has got to be positive, greater than 0. So I've taken my b part, 10k minus 6, there it is, and squared it for b squared, minus 4 times the a part, the 1 plus k squared, times the c part, the 9. Okay, so it's greater than 0. Expand this bracket in the usual way and expand this down here, and you should get this line. And I'll group up my terms. K squared terms come to 64k squared. The k term is minus 120k. These two constants cancel out. So we've just got this simple equation here. So I'm going to factorise it, pull out 8k, and then you're left with 8k minus 15 is greater than 0. Now, when you're solving a quadratic inequality, you should find the critical values. That's where this would equal 0. So that's when 8k equals 0 or k equals 0 and this factor equals 0. So that would mean that k would equal 15 over 8. And then I would draw this quadratic function. I've drawn a sketch graph of it. It's a positive k squared, so it's going to be U-shaped. And we know that it goes through the origin and it goes through this point 15 over 8, 15/8. So I'm looking for where that graph is positive. And I can see that's where it's this branch here above the k-axis and this part of the curve that's above the k-axis. So that means that I need values of k that are less than 0 and values of k which are greater than 15/8. And that's giving us our two ranges of k. You can see that k being less than 0 would be for lines that are having a negative gradient, like this blue line here, and for values of k greater than 15/8, a positive gradient, they'll be represented by this brown line here. Okay? Okay, so this is the last question, quite a long question on the paper. We're given this curve C, which I've sketched here, given by this equation, y equals 32 over x squared plus 3x minus 8, where x is greater than 0. We're told that we've got this line that's perpendicular to the curve at the point P, 4, 6. We're also told that this line here is the line x equals 2, and we've got to find this shaded area, which is called R. And you'll notice I've divided it up into two parts, R1 and R2, because in order to find that area R, I'm going to work out those two separate areas. Now, as I say, it's quite a long question. I'm just going to tell you the method that I'm going to use then as we work through this, so you can get an idea of where I'm going with this. What I'm going to do first of all is establish the gradient of this line L. And I can do that by working out the gradient of the tangent to the curve at this point P by differentiating the equation and then using the perpendicular gradient rule to get the gradient of this line. And once I've got that gradient, I'll be able to find the point of intersection of this line with the x-axis. Okay, I'll show you how we do that later on, but I'm going to call that point x1. So we're going to find that point x1. And then I'm going to work out the area of the triangle R2, because we'll be able to know this base length. Remember, we've got this point here, x coordinate is 4. So we've got this length once we found x1. We know the height of the triangle is 6 units, so we can use half base times height there and get that area. I'm next going to go on to working out the area R1, okay, and in order to do that I'm going to need to integrate our equation between the limits of x equaling 2 to 4. Do that, I'm going to get that area R1, and to get the final area R, I'm going to add these two results together, and we have to show that that area comes to 46. Okay, so that's our method. Let's start. Okay, so I said we're going to find the gradient of L, and we do that then by working out the gradient of the tangent to this by differentiating y with respect to x. So I've changed 32 over x squared to 32x to the power minus 2, and then differentiating in the usual way gives us this. I've cleaned this up, rewritten it as minus 64 over x cubed, And we're looking then for the gradient of the tangent at this point here where x is 4. Substitute 4 then into here and you end up with 2, a gradient of 2. So we want the perpendicular gradient, so that's going to be the negative reciprocal of this. It'll be minus a half. Remember, the product of two perpendicular gradients should come to -1, which they do. Okay. Now I'm going to get this point x1 by considering the gradient now. Remember, the gradient is the difference in the y coordinates divided by the difference in the x coordinates. So at this point here, the y coordinate is 0. Okay, so I've done 0 minus 6, the y coordinate here. And then I've divided that by the difference in the x coordinates, x1 minus the 4 here. Okay, x1 minus 4, and equated it to that gradient, that perpendicular gradient minus a half. And working this out, multiplying both sides by 2 and x1 minus 4 gives us this equation, which you can see by adding 4 now to both sides gives us x1 is 16. Now you could get this value, by the way, if you just worked out the equation of this line using this gradient, using y minus y1 for instance equals the gradient times x minus x1. That would be y minus 6 equals this gradient m times all of x minus 4, and substituted y equal to 0 in it, you'd find out what that coordinate was. It will turn out to be 16, an alternative way, okay? But I think this is much quicker. That's why I didn't go down that route. Okay, so now we've got that, we're in a position to work out then the area of this triangle. Okay, so let's just update this. This point here then is x1 is 16 units across. Okay, so when it comes to working out the area of R2 is going to be half the base, 16 minus 4, 12 units then, okay, times the height of the triangle, which is going to be that 6 there. Work that out, you got 36. Now we need to work out the area R1, and I said we do that by integrating our equation here and integrating it between the limits 2 and 4. So I'm going to need to remove this method here. So if we remove that, give us a space, then to work out that area, you can see I've integrated our equation, or I'm going to get ready to integrate it, between the limits 2 and 4. So in the usual way, if you add 1 to the power and divide by the new power, you're going to get this term here for 32x to the minus 2. Add 1 to the power minus 1, divide by the new power minus 1. For 3x to the power 1 becomes 3x squared over 2, and for the constant minus 8x. Start to put 4 in first of all for x, and you'll notice that I've brought this x down, minus 32 over x, so it's minus 32 over the 4 when it's substituted in. Substitute 4 in here and 4 in that term, and then it's minus what you get when you substitute 2 in to those, and you get this. Turns out as minus 16 for this square bracket minus this result, which is minus 26. I leave you to check that. Comes to 10 units. So that means that if we add those two areas together, then the area of R turns out to be 46. 46, let's just put units squared, okay, because it is an area, okay, units squared. So that brings us now to the end of this paper. So I hope you've been able to solve any problems, get help, whatever, from the paper. What I'd like to say though is it'd be great to have your support. Do subscribe please to my YouTube channel, and then you'll get updates of when I put up other stuff. So good luck, and hopefully catch you in another video.